It's not great, but it's okay. We'll try not to change tabs. I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for the break, and just pray that you'd help us to finish this course well, Lord. In your name I pray, Lord Jesus. Amen. All right. So this is what I did last time, sort of. Well, for the most part, I think I haven't changed much. We talked about space-time, right, and or time-space, really. And of course, we multiply the zeroth component. We put a c in there, so ct is x0. And so that's a typical Lorentz matrix. The one that gets the most airtime there is the x boost, right? And there's the formulas. This page almost fell prey to Thanksgiving libations. Like there was a drop of water that flipped off someone's cup and landed here. And then I was like, I almost did this before I scanned it. I almost did this, and I was like, whoa, wait a second. So I went over and I got a tissue and I blotted it, and I saved it. So I'm very proud of this, but maybe too proud. But anyway, so the Minkowski product is a generalization of the dot product for spacetime, where what? Dudes, no. Oh my goodness. Why am I just seeing that now? I have put the minus here and plus on this and everything else. Why is that there? Oh! Anyway, maybe I should have resisted the urge and just smudged it all out. It would have fixed it. There is a choice that can be made here, right? And depending on which book you read, beware of this. Some people put the minus on the time. Some people put the minus on the space. I like putting minus on the time because then, in as much as your vector is just spatial, the Minkowski product just becomes a dot product, plain and simple. And there's something nice about that. Hopefully, this is a one-off in terms of typos in my notes. So the Minkowski product gives rise to several constructions, right, which will be crucial to formulate physical law within the context of special relativity. Einstein's axioms are our basic guide rails. One, speed of light is constant in all inertial frames of reference. And two, the laws of physics can be written, excuse me, in a form which is the same in different frames of reference, all right? So axiom 1 is enforced by Lorentz transformations. Axiom 2 is put into place by writing physics in terms of covariant and contravariant things which are summed over. Ah, look, yay! Minus on the time, plus is on the space, yay! So maybe it's just that one page that I've got the evil sign error. So this is the Minkowski metric. And there's some formulas for it. Now, the above is simply notation. Here's a nice labor-saving notation. You could write it like this, or like that, or like that. And where's my up-down? Oh, the up-down's next. This is an incomplete thought. It's completed on the next page. With the up-down, well, I eventually will get to it. So I'm like, all right, so what is more abstractly a Lorentz transformation? It's a Minkowski metric preserving transformation, which is linear. So when you work out what that means for the matrix of such a transformation, it has to satisfy this equation. All right, and so such a matrix is called a Lorentz matrix, or sometimes it's just a Lorentz transformation because we typically freely interchange the concept of transformation and its matrix. Right? So there's the calculation. Two coordinate systems are said to be inertially related if there exists a Lorentz matrix which transforms one coordinate system to another. So this is what we mean by inertially related, is that we can get from one to the other by a Lorentz transformation. So this incorporates x boosts, y boosts, z boosts, rotations, and combinations thereof. These are all Lorentz transformations. And notice the notation. I think you know this notation I started talking about last time. Talk about it again. So I'm using primes for the transformed, transform system, and unprimed for the original one. And so, like, you notice how that goes. Now, on the other hand, if I write unprimed, and then I'm going from primed to unprimed, then that's the inverse transformation. And these actually have to be inverse matrices, as I proved down here, by plugging one into the other and working through it. Now, I think last class I did this in terms of like partial differentiation, but these arguments stand alone without any kind of reliance on advanced calculus. You don't know, okay? Or do you know? Maybe, probably. I'd be optimistic. Yeah, you guys know. But anyway, so that is this. And then I can transform this to the prime again, right? But that has to hold, but then rewriting that side to this by changing it to there's a summation over nu prime. Anytime up-down index is repeated, it's a sum. There's a sum from 0 to 3, right? We're using the Einstein summation notation. And so since this is equal to that for arbitrary, x bar nu prime, it follows that this matrix and that matrix have to actually be the same component by component, which is nothing more than saying that these are inverse matrices. Because when you multiply them, you get the identity matrix. Now, the notation is a little bit unfamiliar, right, because of my use of up-down indices and such. But that's what we just did here. So finally, the contravariant for a vector is an object which transforms like coordinates, whereas a covariant vector is one which transforms inverse to the coordinates. So specifically, if we have this is our rule for transforming x bar to x bar, right? Then A is a contravariant for a vector if it transforms the same way, okay? And likewise, it's a covariant if it transforms inversely. So if we have, like I said before, this is the coordinate transformation, but notice that the components of the covariant vector transform by the inverse matrix. Okay. And all right, so these will be, as we'll see today is the next lecture, right? That we can contract a covariant and a contravariant thing and get a scalar. And there's also the index juggling, as it's sometimes called, index gymnastics. You can do things like raise the index or lower the index, well, other way around, right? This is lowering the index, this is raising the index. So we use either the Minkowski metric or the inverse metric. Now, what's the inverse matrix to -1, 1, 1, 1, 1? It's a diagonal matrix. How do you invert a diagonal matrix? You simply reciprocate the diagonals. Like if you were to invert the matrix 2, 3, 4, or suppose you were to invert the matrix 6, 7, 6, 7, then you would have 1/6, 1/7, 1/6, 1/7 as your inverse, right? For example, just to pick a random number. But sorry, I'll eventually get it out of my system. I'm just trying to do it so much that we regret ever doing it, so that we're going to I'm trying to saturate the joke, flood the zone, so that everyone stops doing it. I'm doing my part.
That's horrible.
Yeah, I'm trying. So, anyway, so this is raising and lowering indices, which is, to the math major, a bizarro thing. But to the engineering major, should just be kind of like, math jargon, whatever, we can deal. Now, I was personally, this is what drove me to my advisor as an undergraduate. I kept asking my special relativity professor, what do you mean raise and lower an index? What are you doing? What is that? And he's like, this is the definition. This is just a thing we do. And basically, I just kept coming back and asking him and over, and he just never give a satisfaction. Finally, about the third or fourth time we asked him, me and Crazy Paul, He's like, you know, there's a professor over in the math department named Dr. Fulp, and maybe you should go talk to him. And I was like, oh? And he's like a math physicist and stuff. And I'm like, oh, okay. So I went and talked to him, and I asked him, you know, what was a tensor? And he's like, which kind? And I'm like, okay, now I'm in the right place. So little did I know that would be my PhD advisor. But anyway, so this is like the major theorem we're using today to solve physics problems, which is that if we contract a covariant against a contravariant object, that quantity is a scalar, which is to say, to be more precise, it's an invariant. If I calculate it in one frame of reference and another inertially related frame of reference, it's the same constant. The proof of that is given right here. So like if I have, you know, so here I'm doing some groundwork to figure out that the inverse to a Lorentz matrix is actually this. That's a formula for the inverse of a Lorentz matrix. I actually don't know if that even matters. I decided against it because I realized that I was relying too much on matrix calculation, which kind of makes it all fuzzy. And I was like, all right, fine. I'll go back to basics. To not try to reinvent the wheel with matrices at the moment. So like here's a gory index notation proof of what I'm claiming. So x bar, y bar, the Minkowski product of x and y, is by definition of that. And so let's see here. Oh, I'm sorry guys, I've lost track. Oh. I think what this calculation means is that to say x bar, to say the Minkowski product of x and y is equal to the Minkowski product of x and y transformed is equivalent to insisting that this equation hold for the Lorentz matrix. That's the point of this calculation. It made sense when I wrote it. But how does that help us? Well, all right. So I have AB contracted like this, up, down. So that means I've, lowered the index of B, right? And then I'm trading my G mu nu for a corresponding expression with the Lorentz matrix of that transform us to the prime frame. All right? And then what I'm doing, so I'm keeping one of them with the A and the other with the B, like that. Now this of course is A bar mu prime, and this is just straight up B bar mu prime by the assumption that it's a contravariant vector. That's by definition of contravariance. And this is also by definition of contravariance of A, right? So then notice that I can lower the index like that, right? So what this shows is that, A dot B and A bar dot B bar are equal, provided that the Lorentz matrix satisfies this equation. But this equation is equivalent to the definition, basically, of Lorentz transformation that I derived earlier in this lecture, namely that lambda transpose G lambda is equal to lambda again. I think the calculations are all there, but I'm kind of dumb today. So now I think what I did in class was this. I used a chain rule. This is my chain rule argument I showed you guys in class, which is both better and worse. It's better because it's not specific to the Minkowski metric, and it's worse because it's not specific to the Minkowski metric. Anyway. Okay. So finally, the invariant interval and space-time translations. I said some words about this last time, but I thought it'd be good to revisit it. If we have a point in time space, CT, X, Y, Z, That's an event, all right? A time and a place is an event. And if we talk about two events, say x and y, we can look at the invariant interval between the events. And so that's just like the space-time displacement, right? The inner product of that with itself defines the invariant interval. And so it works out to this, right? Minus the time difference squared plus the spatial differences squared. If we use this notation, c delta t, delta x, delta y, delta z, the invariant interval is minus c delta t squared plus this, plus that squared, plus that squared. This is actually very interesting because this is the heart of all the weirdness that you guys probably did talk about in your modern physics course if you had it. Right? You probably focused on this, like simultaneity no longer makes sense, right? Like delta t can be 0 in one frame of reference, but it doesn't have to be 0 in another frame of reference, which is to say the notions of two events happening at the same time, we lose that in special relativity. And it's not just a, question of observational deception. It's a reality that they really are not simultaneous in two different frames of reference necessarily. Now, if they're at the same point, then I think you lose that. You still have simultaneity at a point, right? Whatever that means. But anyway, so there's all of the stuff I don't want to talk about is all solved by this thing, all right? The Barn paradox, the twin paradox, all that stuff. It's all this invariant interval. And so if we apply the theorem I just worked out for a general contravariant vector to the invariant interval, we get that it's invariant. Because after all, the coordinate is a contravariant vector. Does the coordinate transform like a coordinate? Well, yeah, it's a coordinate. So it's kind of inescapable. But this is, stupidly useful for solving a ton of problems. And then, of course, space-time translation is if you just add a 4-vector to your coordinate. And, of course, that is going to trivially keep the invariant interval the same, right? Because, well, the vectors cancel. So you just have, if you shift by adding, then you shift both of them the same way, then the difference cancels. So just like if we take points in 3 dimensions, right, and we translate them by the same vector, the distance between my the displacement vector between my fists stays the same if I translate both my fists by the same, right? This is just that adding time to the mix, a space-time translation. Now the Poincare group is the set of origin, so it's like the set of origin fixing Lorentz transformations paired with the space-time translations I just talked about. This forms the Poincare group. These are all transformations which leave the invariant interval between all pairs of events in Minkowski space fixed. So it includes Lorentz transformations, but it also includes space-time translations. It's technically a 10-dimensional Lie group, of which the Lorentz group is a 6-dimensional subgroup. And there's all kinds of interesting mathematics here. So the rotations of space fixing time are Lorentz transformations, also rotations of space fixing time. Oh, yes, rotations of space fixing time. Those are Lorentz transformations. Those are just rotations, all right? Rotations is what the first sentence is about. And also x boosts, y boosts, and z boosts are also Lorentz transformations, and hence in the Poincare group. So I think one of the problems I had give you guys in your assignment is to actually show that these guys actually solve the necessary matrix equation. And that is just what it sounds like. You just multiply the matrices out. It's not especially exciting, but it's not especially difficult either, and it should work out. Unless you make an error like I did. But you won't do that. So, all right. So, I will force myself to write things out for you guys now. But beware, I'm not playing with a full deck today, so if you see something, say something. You know what I mean? So this is lecture 38. I'll give you about 5 minutes to clean the board. So I want to talk for the rest of today about 4 vectors in physics. So I'm talking about how do we actually write down physical law equations in terms of special relativity, like how do we do this? And hopefully we'll look at some problems of momentum conservation. How's that work in the special relativistic sense? I have 3 interesting examples to show you there. So we'll see. So I've been talking about contravariant and covariant vectors, right? But I haven't really given you any examples except for the, the ultimate example of telling you that we can put the voltage and the vector potential together to make a so-called 4 potential, right? I kind of put the cart before the horse there. So what I want to do now is to kind of go back and just show you basic 4 vectors that we can construct for the motion, corresponding to the motion of a specific particle. And we'll think about the particle being massive to start with, at least. So if I can find a marker that works, then we'll be in business. All right. So before I realize I've left the projector on the wrong setting, let me, oh my goodness, it was really bad. All right, there we go. So I was just telling you about the invariant interval, right? But what we'd really like to think about is the infinitesimal invariant interval. ds squared is minus c squared dt squared plus dx squared plus dy squared plus dz squared. This is often referred to as the invariant interval. And the usual starting point here is to consider some object and imagine a co-moving coordinate system with the object, right? So if you did that, right, a co-moving coordinate system with the object, what would dx and dy and dz be for a co-moving coordinate system? I mean, I think you can agree with me, it should have dx, dy, and dz all being 0, right? If the coordinate system is moving with the particle, then those should be 0, right? And so in that case, we call time in this system the quote-unquote proper time. And actually, we essentially, by definition, say ds squared is equal to minus c squared d tau squared. D tau is the proper time. All right? And so we like to parameterize the world line of the object via the proper time. The argument is that we can do that, and if we do that, how does that work? So, all right, so I'm already, all right, so you got some object, it's moving along however it is, right? And so this point would be like x prime, not x prime, x, y, z, all right? All right? If I use my usual Calc 3 picture, right? So you got some trajectory, and we want to kind of take stock of d tau squared, the invariant time squared, right, would be ds squared over minus c squared, right? But this ds squared is the invariant interval. So it's the same for the proper co-moving frame at an instant as it is for the fixed inertial frame of reference we're measuring, the xyz coordinate frame. So I can say that that's equal to minus c squared dt squared plus dx squared plus dy squared plus dz squared, all divided by c squared, right? And so what that gets me then is that if we divide the equation by dt squared, we get d tau squared divided by dt squared. All right. What row? Oh, it's here. Thank you. So dividing by dt squared gives us a 1 minus 1 over c squared. And I'll write this as dx over dt squared plus dy over dt squared plus dz over dt squared. All right. So definition, u vector is just going to be the ordinary velocity with respect to the xyz, txyz frame, all right? So u vector is the velocity of the object. It doesn't have to be constant, it could be variable, all right? But at an instant, it has to be related to the proper time according to this rule, at an instant. And so what you see we got is that this is what this equation up here gives us what? It gives us d tau, oh man, trash. D tau, much better. D tau squared dt squared is equal to 1 minus, what is that? That's u squared over c squared. And then, yes?
Do you mean to put the squared on the d instead of the tau? I guess that's kind of notation, but it's d tau squared. Or do we literally mean d tau quantity squared?
I mean d tau quantity squared, yeah. So I want for this to be, I see what you're saying, but d tau dt quantity squared, actually. So what we have then is that d tau dt is equal to the square root of 1 minus u squared over c squared, which then gives us that oh goodness, d tau divided by the square root of 1 minus u squared over c squared is equal to dt, right? And this, gamma, and if you want to be gamma of u, which we'll just write gamma because we're going to write that a lot. So if there's ambiguity, we'll denote the dependence. I mean, you can write down a gamma factor for any velocity. I mean, for any speed, really. But we're going to be talking about gamma subject to u here for the most part for a little bit. And so this equation just becomes gamma d tau is equal to dt, which has an interesting physical meaning. It means that the time that an inertial frame of reference measures as having expired for a particle is longer than its proper time, right? Because if gamma was 10 and I had 1 second for d tau, I would have 10 seconds for dt. And this is actually one of the ways that we knew experimentally that like special relativity was probably right a long time ago, back even in the 40s, 50s, whatever. I'm not sure when this happened exactly to start with, but we had these so-called bubble chambers that, you'd have a high energy particle, and it would hit, I'm not sure where, but basically you could tell. Let me just get to the end of the story. So essentially what we did was we saw nuclear reactions that indicated that a certain kind of particle existed as a consequence of other ones slamming into each other, right? But those particles lasted a long time relative to how they last. If they're like in a lab frame, just sitting there and stuff happens, maybe they last like a microsecond. But we were seeing trajectories where they would last 20 microseconds or something. So it's like, why is that last 20 times longer when it's moving much faster? Well, this is why. So like that's one of the experimental confirmations of special relativity. It was necessary to understand how long particles exist after they, come smashing out of other particles and stuff. But okay, so definition. U mu is equal to d x mu d tau. So this is the 4 velocity, aka the proper velocity. All right, and so let us work out what that is. So this is, let's see, we just figured this out. We can trade a tau for a t how. What do we do? This is like d
Divided by gamma.
So this is like a chain rule, right? dt d tau, dx mu dt, right? And you said that's multiplication by gamma? Yep. That's see this is 1 over gamma, right? So what we have then is, yes, gamma of u, I'll write it down here for a moment, times dx mu dt, but that is gamma of u, and I'm going to write it as a vector. This is ddt of ct, ddt of, if you'll allow me this kind of hybrid notation, save me some writing, right? And so, of course, this is just c, right? So what we get is gamma c, comma, gamma u. So the 4 velocity is gamma times the speed of light, and then gamma times the regular velocity, right? So this is a 4 vector. What's its invariant? Can we get an invariant from a 4 vector? Yes, we contract it with itself. We take u dot u, right? So like u dot u, if I think about these as 4 vectors, in other words, it's, u0, u0, plus, let me just get to the point here, gamma u dot gamma u, right? Which is what here? This is just, minus gamma squared c squared plus gamma squared u squared, also known as minus gamma squared times 1 minus u squared over c squared times, c squared, also known as minus c squared. So that's an invariant. I mean, it's kind of in your face that it's invariant, right? That doesn't depend on the choice of coordinates, does it? C squared is c squared, right? So, you spent a lot of my time in my life talking about, this invariant interval. Who cares? How does it help us solve any problem? You just, wow, so impressive. Speed of light squared. It's constant in all frames of reference. Yay. I promise we'll do something with it. Just give me a second. So next up, you can talk about the 4 acceleration. And that is going to be, shockingly, the derivative of the 4 velocity with respect to the proper time. Now here's your d squared for you. D squared x, I really mean it this time. D squared x mu d tau squared, right? And so if we think about that as a 4 vector, we've got, you know, dt d tau, dt d tau, same trick again, dt d tau times du dt, right? Which is gamma times ddt of c gamma gamma u, right? Which then by the product rule is gamma times, well, c d gamma dt comma d gamma dt times u plus gamma times du dt, right? You might recognize du dt as the what? Acceleration, right. So this is little a. This is just regular acceleration. And by the way, this has no relation to the 4 potential a I used. This is acceleration of a material object. This has no connection whatsoever to the 4 potential. Just same letter, that's all. But people don't usually talk about these 2 different things in the same breath, so it's kind of like, you know, okay. So theorem, if the 4 acceleration has the 0th component a upper 0, and let's call this thing a script a, then turns out that the a upper 0 has to be the velocity dot the acceleration vector. It's not acceleration though, right? That's script a. And I'll get out of the way here in a second. The script a is actually equal to gamma squared times a vector plus gamma to the power 4 of u dot a divided by c squared times u. And that is, what would you think we're going to call script a?
4 acceleration?
No, it's a vector.
Proper acceleration.
Nah, proper acceleration's up there. So this is known as the relativistic acceleration. And I suppose I owe you another term, because I also should have defined for you the relativistic velocity. See here, gamma u is equal to the relativistic velocity. That's what I would call it if I had to give it a name. It's the spatial part of the 4 velocity. Questions? No? Now, claim, if you take the 4 velocity and you take the Minkowski product with the proper acceleration, right? You get 0. This claim and this theorem are for you guys to do. So it's not that hard though. You just need to basically sort through what's being said. And this is half the battle, is just understanding you need the product rule. And basically, to get from here to here, you need to work on what is the proper way of writing d. Notice there's no d gamma dt in the answer. So we're trading a derivative of the gamma factor for an expression with gamma. That's your goal to work this problem. This theorem is to figure out how to get a formula for the derivative of gamma in terms of gamma. If I say much more, I'll solve the problem. This, on the other hand, is much easier. That's like a line or two. All right? Yes, no? No? All right. So with that, let's go on to what's the next 4 vector that you might care about. So you got acceleration, right? The jerk, relativistic jerk. Yeah. You know, I haven't seen that anywhere, actually. I don't know. Yeah, maybe you could be the first. I'm just kidding. There are plenty of jerks in physics. Surely someone's done it already. Let's see here. I'm just kidding. Physicists are great people, but you know, anyway. Try not. Let me try to behave here. So, for momentum is the next. For momentum. How do you think we define for momentum? You say the for mass? No, we just take the for momentum is simply defined to be the rest mass times the proper velocity. And that is specifically m gamma times c comma u, right? Which we could write as m gamma c, m gamma u, all right? And so you're looking at p upper 0 and p. This right here is the relativistic momentum. So the relativistic momentum is rest mass times gamma times velocity. And of course, the relativistic momentum just becomes regular momentum in the limit that u goes to small velocities, right? When u is very small, gamma is essentially 1. We're just back to gamma and, like, you know, mass times velocity is momentum, of course, right? Now, and gamma has the same meaning it did before. But let's just talk a little bit about this.
Is P0 rest momentum?
It's the well, yeah. The question is, what is P0, right? That's exactly the question. So let's work on that. So gamma of u is 1 minus u squared over c squared to the minus 1/2 power, right? And so if we use the Maclaurin expansion or the binomial series, whatever you like, we can expand this as 1, minus 1/2 u squared over c squared, all right, plus dot, 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 binomial series. And so as we look at, like you said, P0 is what? P0 is, well, apparently mc times 1 minus 1/2 u squared over c squared plus dot, 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 right? Apparently that's what P upper 0 is. So it's almost like we know that kinetic energy, right, is what? 1/2 m u squared. I'll put some scare quotes on that because that's the classical kinetic energy. We might need to change that, right? But in the limit of very small velocity, if u is much, much less than c, then this part is tiny, right? Like this approximation becomes a very good approximation in the limits of low velocity relative to c. And of course we know the kinetic energy is a thing there, and it's 1/2 mu squared in my current notation. So to get from that to here, we're missing a factor of c, right? So to make that happen, let's multiply both sides by c. Cp naught mc squared, right? And if I do that, then I've got mc squared minus, hold the phone. There's no minus. How did dudes, come on. That's a plus, dummy. Me, not you. It's a plus. Sorry, that's very offensive. I knew it was wrong because I changed it to a plus in like the next step. But, okay, so mc squared, take that logic for what you will, 1/2 mu squared, right? And of course, what have we discovered? The rest energy, right? So this, of course, we understand, given the weight of history, this is the rest energy. And over here is the kinetic energy. And so I don't even have this in the notes, but if you want to define kinetic energy relativistically, you know what you do? You take, what's that? You solve for it. That's actually it. Yes, you do Cp naught, minus mc squared. In other words, gamma, I think gamma minus 1 times mc squared is the formula for the kinetic. This is the actual honest relativistic kinetic energy. It's everything that's not the rest energy is the relativistic kinetic energy. Yeah.
Is it safe to ignore the further terms?
The what?
Further terms?
That's all in here. Because this P upper 0 is, with times c, it's mc squared gamma. So I'm just solving. I'm just subtracting this to the other side. It's 1/2 mu squared plus the da. So it's tricky, yeah. So if we're massive, so apparently this is equal to the energy, right, divided by c, comma, the relativistic energy, relativistic momentum. What's the invariant interval here? This is a 4-vector. So if we take the Minkowski product of it with itself, right? That's, what is that? That's minus, m squared, gamma squared, c squared. Oh, I don't want to do that. I'm a dummy. I'm an idiot. Look, we're making our life too hard. It's m u bar, right? Dotted with m u bar. How does Minkowski product work? You can factor the m out. So we got m squared u bar dot u bar, right? We already worked this out. What is that? Minus mc squared is what the invariant of this with itself, right?
Where did their m go? Where did it goes from m squared to m?
Oh, thank you. My bad. Now, on the flip side, this is also equal to e squared over c squared with a minus, right? Plus momentum dot momentum, where that's the relativistic momentum, right? That's a physically interesting equation because it means the relativistic momentum and the energy have to be related to the rest energy in this way. This is a non-trivial physical statement between different frames of reference, which we can actually use meaningfully to solve interesting physical problems. Let me show you some of those. Come on. Come back to us. All right, there we go. Come on. Come on. I pressed the button. Acknowledge me. It won't acknowledge. Well, all right, fine. I guess we just have the lights on. All right, so I just worked through this a bit. Now, here's the interesting thing, is that this relation that the form momentum squared should be, minus mc squared. In a limiting sense, this still makes sense for things that have no mass. So this is why we're not surprised to find that light, which has 0 rest mass, right, has to have a relation between energy and momentum. Cp has to be equal to E over c in order to get that that's 0. See, E squared over c squared has to, like P has to be E over c, right? Or E has to be Pc, I think. Yeah. E equals to Pc for light. So this is how we solve light problems, right? We can't put mass, there's no mass, all right? But nevertheless, this is super useful. The energy squared is c squared p squared plus m squared c to the 4th, yeah. It turns out, in a nutshell, that form momentum is conserved for collisions in special relativity. And so we can look at the conservation of form momentum, but what is that? Well, I mean, that's the conservation of energy in the relativistic sense and relativistic momentum, all right? And so here's an example that's very kind of hokey, but I guess in Virginia that's a compliment, right? I don't know. Depends. I don't know. That's outside my sphere, So we've got 2 lumps of clay, which for some reason have been launched at 3/5, 60% the speed of light at each other, and they stick together somehow when they hit, which is really kind of impressive, like so, as you can see. Spent a lot of time drawing that. But so you've got the momentum for A, the momentum for B, form momentum, that is, gamma A, gamma B. Now they're equal since they're both the same speed, even though they're different velocities. So, right, because gamma is an even function of speed. Well, anyway, it works out to 5/4, both of them. So I have the momentum of A plus the form momentum of B is equal to the form momentum of the combined system, which shows me that from the 0th component, from the energy part, we get this plus that equal to that, which is equal to that, where m is the mass of the resulting composite object. It doesn't have to be the sum of the masses. See that? We can't assume that mass is conserved. It's not. All right? It's not. In fact, as we work this out, conservation of relativistic form momentum here says that the mass of the composite lump is actually 50% bigger than we'd expect classically. Some of the energy of those 2 lumps of clay has been converted to mass in the process of them colliding together and congealing. So the energy has become mass. Neither mass nor energy are conserved, but they can change form, one to the other. That's the new thing in special relativity. But again, it's just simple conservation of form momentum. Here's another one. You have a pion, whatever that is, and it decays into a muon and a neutrino. Find the energy of the outgoing muon in terms of the mass of the pion and the mass of the muon. All of these examples are stolen from Griffiths. I decided not to reinvent the wheel. These are examples from Griffiths, but I thought it'd be helpful to see them worked out. So before, we have 0 energy and 0 momentum, right? After, you've got the momentum for the neutrino, and you've also got the momentum for the muon, right? They each have their respective energy and mass. Now, when this example was written, the mass of the neutrino was thought to be 0. It's very close to 0, so this is not too wrong. I mean, it's a pretty good approximation of something else. Anyway, so there you go. Equate for momentum. We get the relativistic momentums have to sum like this, and the energy of the involved are related like so. And now E, the energy in the neutrino is just the momentum times c, since the mass is very, very, very small. And then the rest is just kind of algebra, but you have to actually use that invariant relation between the energy, the momentum, and the rest mass. You have to take that and you can solve it for momentum, and that allows you to trade the momentum in the formula here for the square root of the energy, and then that gives you an equation which just has energy and doesn't have momentum. And after you make that substitution here, then you can like square both the equations and solve, and there's the energy of the muon in terms of the mass of the pion and the mass of the muon in c squared. This is from the conservation of 4 momentum. And a key part of this calculation was using the invariance of the 4 momentum to connect the rest energy to the momentum and the energy in the frame that we're looking at. The next example is known as Compton scattering. Here we have a photon, which I've illustrated with this very carefully drawn wavy line. It comes in and it hits an electron, right? The electron absorbs the photon and then starts shaking around, and then it emits the photon after a short time, right? And after it does that, the photon goes off this way, and then of course the electron has to go off that way. Now, momentum and energy have to be conserved, which means the net motion of this still has to be like that direction, right? And also there has to be a conservation of energy and mass, right, in the sense of relativistic energy. And so that's all expressed in this 1-4 vector equation, right? And then you do some steps and some algebra, and like, let's see here. Of course, for the photon, the momentum is just E naught over c. And we still have vertical and horizontal components to sort through. We've got like the angle sine phi is E naught. Well, I solve this equation for that, and then plug that in to this equation. This cosine phi gets replaced with the square root of 1 minus sine squared phi, which is this. And then I've got this lovely equation, which I'm sure I did something with. There's another page of this. So you return to the conservation of energy, plug some stuff in, and do some algebra. And after a bit, you find that the energy is the reciprocal of, so this is like the energy of the incoming photon, and I think this is the energy of the outgoing photon as it relates to the scattering angle and the mass of the electron, the speed of light squared. Now, if you rewrite this in terms of wavelength, as you can do from quantum mechanics, because we know the energy is the Planck's constant times the frequency, which is also hc over lambda, that equation can be rewritten in terms of the wavelength as this, and this formula is largely known as Compton scattering, which describes the angle dependence in energy of light that comes off an electron which has been hit with some kind of radiation or photon. And then finally, last but not least here, you can talk about for the 4 force and Newton's law in special relativity, and you take the proper time derivative of the 4 momentum, right? That gives you the 4 forces you might expect. Not the 4 forces though, that's something else. Maybe late at the end of the week we'll talk about that. But so again, same trick, convert tau to t multiplied by gamma. You can go back to the thing I'm asking you guys to derive, and Newton's law is, force is equal to dp d tau, and we get this is the formula for the force as it relates to the acceleration and velocity. And finally, back to the problem that kept me from being a PhD in physics, the missing gamma. There it is derived in all of its glory. And it turns out